I know you guys are at many, many different levels. Some of you are starting grad students, some of you are finishing grad students. You may have done different types of grad courses. So I know, and the organizers told me about 15 times, to assume as little knowledge as possible. So I'm basically going to assume zero knowledge in this. So there are many of you who will probably be experts in a lot of this material, seen it before. If so, humble, humble apologies. I'm assuming zero starting knowledge, so if you know stuff, then, yeah, okay, apologies, there we are, all right. That's my round of apologies. So what I'll be talking about are intersecting families, and they're something that's at the heart of extremal combinatorics, or extremal set systems. But they won't get mentioned in the first lecture, because roughly speaking, to get going on intersecting families, there are a couple of basic, very important facts you need to know. And I didn't want to just say, let's assume these facts and carry on. So lecture 1 will be some important things that don't mention the word intersecting family. So don't worry, I haven't forgotten what the course is about. They're defined in lecture 2. But somehow, with lecture 1, I would say this course will then give you a proper grounding in extremal combinatorics. Otherwise, it would be a weird, non-proper grounding. So where we work is this sort of background and important stuff today. Next time, these things called intersecting families. And then the following 3 lectures will kind of push what we know from lecture 2 in different directions. We'll see in each of the lectures things that are very interesting about intersecting families, but they're also linking with other bits of maths in both directions. There'll be some things where we use other bits of maths to understand intersecting families, bits where we use intersecting families to understand other bits of maths. There'll be some things from geometric analysis, like subsets of space, R cubed, RTN, and so on. There'll be some use of algebraic topology. But don't worry, I'm assuming you've never met the words algebraic topology, so I'm not doing anything, but that will come in at some point. So that's the kind of general plan. Also, another apology, I say the word maths rather than math singular. Again, if that annoys you, I apologize. Okay, so what are we studying in extremal set theory? We're studying the subsets of a finite set. And you might initially think that's very silly, because all you can ever say is 2 subsets either meet or they don't. 2 subsets either has A contains in B or not, so that's very, very boring. But in fact, as we'll see, there's a huge amount you can say. It's a very, very rich area. It's an area where there's a famous quote, which is, extremal combinatorics is full of a bunch of theorems that you couldn't prove for yourself in 10 years, and a bunch of one-line proofs of those theorems. Now, that's not quite true, but it is true that a lot of the theorems, the proofs, are exceptionally ingenious. So don't be fooled. If I do a proof here and it's short, I will, of course, stress, yeah, here's the key bit. You guys are supposed to go back and think about what was the clever bit and so on. I'll be talking in seminar format rather than undergrad lecture books. I'm not going to write full sentences. I write as though it was a research seminar. There are printed notes for this course, which do have full sentences and everything written out. They're available, or available later today, via Hoover. There'll be a link to the printed notes, which contain everything I say. And at some points, I might say, it can easily be checked that. And then the printed notes will either check it, or they'll also say, it can easily be checked that. You just have to live with that. All right, so what's the thing we're studying? We're studying the subsets of a finite set, set of size n. So I'll always write capital X for the set 1 up to n. Then we have the power set of X. That's all subsets. You can write a curly p, whatever you want to write. So that's all subsets of X. And we're interested in understanding subsets of that. So we're interested in understanding collections of sets. So the first question is, how should you draw this? How should you draw a collection of sets? And here's how not to do it. You don't want to say, here's my ground set X, and I have some sets, an A, a B, a C, and a D, because you'll never see what's going on. Once you have more than about 3 sets in your family, you cannot see what's going on. So that's never going to be the way to visualize a family of sets. So how should we visualize it? Well, it turns out to be very convenient to make this into a graph called Qn, the discrete cube. And the way you make it into a graph is you join two sets if they differ in one element. So for example, the set 1, 2, 4 is joined to 1, 2, 4, 7. Just by the way, life is too short to have huge piles of commas and set braces. So 1, 2, 4 means the set 1 and 2 and 4. And I promise, and I've checked, I will never ever have a set with 10 or more elements in any example. So this will never be ambiguous. Okay, so let's have a look. Let's have a drawing of it. I guess Q2 is quite boring. There's the empty set. There are two singletons, and there's the whole world. And remember, you joined things different one place. So joined, joined, joined. So it's kind of like a square. So that's Q2. Let's try and draw Q3. So there's a dot for the empty set. There are the three singletons. The three pairs, and the whole world. And I guess emptiness is joined to each singleton. 1 is joined to 1, 2, and 1, 3. 2 is joined to 1, 2, and 2, 3. 3 is joined to 2, 3, and all the pairs joined to everything. Something like that. Okay. And if you squint and look at it the right way, you see a three-dimensional cube, right? And why is that? Because you can draw it as a cube. So I'll write equals. Let me draw an actual three-dimensional cube. So this is supposed to be the set 0, 1 cubed living in Euclidean space R cubed. So if I think of the directions as directions, say 1, 2, 3, I could think of the point 0, 0, 0. That's like the empty set. Then 1, 0, 0 is like singleton 1. 1, 1, 1 is like the point 1, 2, 3. The point 1, here is 1, 1, 0, which corresponds to the set 1, 2. Is that making sense? So for each set, the set 1, 2, 7 is a zero-on sequence that's 1 in positions 1, 2, 7, 0 elsewhere. And the rule that says you join differ one element corresponds to you join two zero-on sequences if they differ by 1 in exactly one place. And it's incredibly important to have both those points of view. If you're stuck on just one point of view, some things will seem hard that are easy with the other point of view. How do these things generalize to n dimensions? Well, this one will generalize something like this, I guess. You have a little dot at the top, another level, getting bigger and bigger. The biggest is the middle. You're supposed to sort of know that binomial coefficients, mumble, biggest in the middle, mumble, and then they go down again. I guess officially I should say that's in the case where n's even, right? If n is even, then that's the middle layer. Of course, if n's odd, there are two middle layers equally big, right? Like 7 choose 3, 7 choose 4, the same thing. So I'll draw it like this. I really mean there are two cases. And just for notation, often you want to say take all sets at level R. You might write this as x brackets R. So x brackets R means I'll say all the R sets. So x brackets 2 means all the 2 sets, and so on. So it breaks up into levels. So another way of saying this is the biggest level is x brackets n over 2. How do you visualize this one, high dimensions? Well, it's quite hard to draw, obviously. I could draw you a Q4, but I won't. A Q4, I guess you'd have a Q3, another Q3 above it for the fourth coordinate, and things are joined vertically upwards. They get kind of hard to draw. And in fact, part of the problem with the whole area, it's very hard to visualize stuff because, okay, you can draw a 3D picture, but obviously there's no question that's interesting about the collection of all subsets of a 3-point set. Once you're up to about 5 or 6, your picture, you cannot draw a picture, you can't visualize it. So that's part of the problem. We're interested in things not for some tiny n, but for all n, or for n large, and so on. So these pictures are nice to have, but somehow the problem is you have to remember that n is big, so we're in a high-dimensional space. Okay, that's Qn. Now, what are we going to ask about Qn? Well, here's something you could ask. You could ask, how tightly can we pack a subset of Qn. So intuitively, I'm saying to you, I'd like you to pick so many points, 17 points in Qn. How should you pick them to be as tightly packed as possible, whatever that means? Now, you may have met this in the continuous setting. So many of you may know that, for example, in the plane, so in R squared, if you look at all sets of a given area, it's the disk that has the smallest perimeter. Right, so for example, the disk beats a weirdo shape like this. Again, sets of a given area, which has the smallest perimeter, the answer is this one. That's sometimes called the isoperimetric inequality in the plane. And you can rephrase it, you can say a curve of given length, what's the biggest area to enclose? That'll be the same statement, and the answer will be a circle. You could ask the same thing in R cubed. You can say in R cubed, amongst objects of, now of course, a given volume, which has the smallest, now its surface area, and you may or may not know the answer is a sphere, a Euclidean ball. So it's hard to draw. Euclidean ball, that beats other shapes. And that's why, okay, now comes the physical excitement bit. The one time I ever mentioned the real world, this whole series of talks, that's why soap bubbles are circular. Right? Because in a soap bubble, because of surface tension, it wants to have the smallest surface area. It's enclosing a fixed volume. So that's very cool. Okay, end of physics. But you're supposed to know this. You're supposed to know this. Okay, and so on in higher dimensions. Actually, a lot of these were kind of proved in the 19th century, but the proofs were wrong. The proofs tended to say, assume there is an actual minimizer, then ... but they didn't address the question of why there is a minimizer. In the 20th century, people were using things like compactness arguments, and if we made rigorous. But if you go and look at some old-fashioned proof of one of these in an old book, it'll say, take the winning set and will never address the question, is there a winning set? Of course, for us, that's never, in the discrete world, of course there's a winning set, but only find many sets, so that'll never arise to us. You can ask the same thing on the surface of a sphere. You could take the surface of the Earth. You could take S2 living in R cubed. So by S2, I mean the surface of the sphere. So this is the world we're living in, the Earth. And then the question would be, among subsets of given surface area, which has the smallest perimeter? And you would guess, and you'd be right, that the answer is a circular cap. So a circular region, or if you prefer, you cut the sphere of the hyperplane, and it's what you a bit there. So circular cap is best. Those are all continuous. What would it mean in a discrete setting? Well, let's do it in, say, you can do it in any graph. Let me do it in, say, the cube, because that's what I really care about. So the question would be, among subsets A living in Qn, so sets of vertices, with a given size, which one minimizes what you might call the boundary of A. Now, what should the boundary mean? In the continuous case, it's obvious, it means the boundary. In the discrete case, I guess there are two things it could mean. So if I had some general graph over here, here's some graph I'm living in. If I said to you, is yellow visible? Not quite, okay. Is red visible? Is it also clear that red is different from white? Okay, great. So suppose I had these 3 points here as my set. Suppose that was my A. There are two things the boundary could mean. It could mean the vertices adjacent to A but not in it. So that'll be like this one and this one. And that's normally written B of A, B for boundary of A. You could also say, no, I'd rather say the boundary is the edges that leave the set. That's just a different story, which isn't going to concern us, but it's also an interesting question. So for us, boundary of a set means the points adjacent to it but not in it. And it's often a little more convenient for doing calculations to work instead with the neighborhood of A. And the neighborhood of a set means the set with its boundary. So A union the boundary of A. So in pretentious language, you could say it's all points at graph distance at most 1 from A, if you like. Okay. So which one minimizes the size of the boundary of A? It's a very natural question. What should we do? So I'm giving you, 17 points in Q6. What should you do? Of course, you want them clumped together, not too far apart, right? But there are many ways to clump something together. Just as in Euclidean space, it could have been a square or a triangle or a circle that was best, until you thought about it a bit. So let's try an example here. Let's try, for example, size of A is 4 in Q3. So I'm asking you to take half of Q3 as tightly packed as possible, meaning boundary as small as possible. I think there are two obvious sets of size 4 in the cube for any problem. One would be to take a kind of metric ball, to take a point and its neighbors, right? So I could write that as x brackets at most 1. So just as x brackets r means all sets of size r, x at most r means all sets of size at most r. So this corresponds to a point and everything one way from it. Right? That sounds like a good guess, by the way, because notice in all these examples, in all of them, even on the sphere, the winning set's always the following form: pick some point, then take all points at distance at most r from it. So they're always metric balls. That's an interesting thing. But also, there's another thing in a cube, you can take a half space, right? After all, Q3 contains beautiful Q2. So, or we could have a half space, like the bottom of 4 points. Two obvious guesses. Okay, which has smaller boundary? Well, this one's rubbish, right? It's got all 4 other points within the boundary. This one has only 3 points in its boundary. The set's of size 2. So this wins. And if you go ahead and did lots of examples, you'd convince yourself, correctly, that those metric balls are always best. So that seems like a good thing to do. Okay, so things of the form x at most r seem best, I'll say. Okay, what if you're between 2 layers? So supposing, so here's my entire cube in levels. Here's Qn. I've got up to level r. But actually, the number of points you had to pick was a few more points. Right? You have to pick 5 more points. You do all sets of size at most 3, and 5 more points. Now, it's very natural to guess you put them on the next level, right? That obviously is good because they have small boundary. So you'd want them all down there. But how would you want to put them? So we've got some points to pick on level r plus 1, let's say. We want them tightly packed, presumably, themselves. There are 2 obvious things you might want to do. You might want to say, on a given level, let's use coordinate 1. So take sets involving element 1. That'd be a good thing to do. Or you might say, let's do everything avoiding element n. Right? Those are different kind of things. So let me try and motivate it by a kind of fake motivational picture. So just imagine for a second that we're in 3 dimensions, but somehow you're not living on the discrete cube, but in the continuous cube. Close 0, 1 to the n. Okay, now, let me draw the piece of this, which is, so that triangle is the place where the sum of the coordinates is a fixed number, right? So x1 plus x2 plus x3, I'll say equals r. That kind of corresponds to sets of size R in some sense. Now, supposing I said to you, this continuous world, I want to pick some blob in that slice, but I want it kind of really, really tightly packed. Here are some choices. You could say, I'll take the things with the first coordinate, say third coordinate, doesn't matter, third coordinate big. That would be like a region like this. Is that making sense? Everything with third z coordinate big. Or you could say, I'll take the z coordinate small, that's more like that, isn't it? Making sense? On the bottom. Which is more tightly packed? Well, clearly that one's more tightly packed. Okay, that doesn't prove anything about the discrete case, but if you check it, that's actually correct in the discrete case. So what you do on a level is, you go for use a coordinate, not don't use a coordinate. Right? This bit here says, please don't use coordinate 3. Let x3 be 0, or close to 0. This part's saying, please use x3. Okay, so that suggests a kind of ordering for the points on level R. The rules would be, please use element 1. So all R sets with 1 before all the others. And then, given you've got a 1, what's your ordering? Please use element 2, and so on. So that's called the Lex order on XR. And the rules are, you use small elements. So I'll write as a slogan, use small elements. So as a formula, you could say that x comes before y if you go along, do they both have 1, neither have 1, both have 2, neither have 2? The first time they disagree, that's the earlier thing, right? So a set that starts 1 and 2 and not 3 is later than 1 and 2. So you could write that as minimum of, I'll write x delta y for symmetric difference. The points in exactly one of them belongs to x. So the first time they disagree, it belongs to x. So for example, if I did 4 brackets 2, so 2 sets from 4, there's 6 of them, right? We start with everything involving a 1. And amongst the things with a 1, we make the next element as small as possible. So we'd go 1, 2, then 1, 3, then 1, 4. We've now run out of things that start with a 1, so we're forced to now start with a 2. And amongst things that start with a 2, please make the next element small. Right? So 2, 3 comes before 2, 4. And then last of all, you get 3, 4. So that's Lex. Whenever anyone mentions Lex, they also mention colex, kind of the opposite notion, which I will mention, it's going to come in as well in the story. So while we're here, let me just digress and mention colex. So colex, again on x brackets R, the rules are, please don't use big coordinates. So it's more like that one. So in colex, you don't care how it starts, but everything without an n comes from everything with an n. Or put another way, look at the last time they differ, it belongs to the bigger thing. So in this one, it is x less than y if the biggest time they differ belongs to y. Let's try example on 4 squared. So what are the rules? You start off keeping the biggest element of small, that could be a 2, right? The biggest element could be a 2, so that's 1, 2. Okay, that's everything that ends with a 2. What do you do next? You do everything ending with a 3, because you want it to end as early as possible. Don't use a 4. So now come things end with a 3, and amongst those, you keep the next element small. So 1, 3, then 2, 3. And now we're down to things that end with a 4, so you do those, again, in what order do you do them? In order of the second last element, either first element. So 1, 4, 2, 4, 3, 4. So note, colex isn't lex. Because, for example, 2, 3 is 2, 3 versus 1, 4. Colex would say, that involved a 4, it's later. But lex would say, we love 1, 4, it involves a 1, it comes before 2, 3. So not the same ordering. And they're kind of the same ordering if you take complements. So if you think about it, lex on xr, if you then complement it, gives you colex on x n minus r, but with the ground set ordering reversed. I'll sort of say it in words. Let's sort of say it in words. So if I tell you on some level x is before y in lex, that means that x has a small element, right? So in the complement, that says x avoids that small element. If you reverse the ground set order, that says it avoids the big element. Okay. So in other words, if I said to you, here's a drawing of the first 7 things at this level in lex, what it looks like is colex on the complements, except you reverse the ground set. Okay, so they're not the same ordering, but they're kind of lex in this level looks like colex in that level. Okay, so what we're saying back to the cube is that you go up in levels, and then on a level you use the ordering. Remember, we said we want to use an element 1, use an element, not use it. So that's going to be lex ordering, and that in total is called simplicial ordering on the cube. So sorry for the barrage of names. This is the last one. Simplicial order on Qn is defined as you go up in levels, as we were doing in our pictures, and on a particular level, you go lex. That seems to be what minimizes the boundary. So x is less than y in simplicial if either size of x is size of y, or they have the same size, but x is less than y in lex. So again, you go up in levels, and inside a level, you want to use coordinate 1 if you can, and so on. And what you seem to be suggesting is that that's best for solving the isoperimetric question in Qn. And that's true, and that's our first main theorem, and that's called Harper's theorem. So here is Harper's theorem. Let A live inside Qn, and then what we're saying is that the best A you could have taken would be the first that many points in the simplicial ordering, right? So let's say, and let's say C be the initial segment of simplicial. Initial segment, which means the first so many points of the same size. Okay. Then the neighborhood of A is at least the neighborhood of C. Okay? So we're comparing our unknown set of 17 points with the first 17 simplicial ordering, and the claim is that one always wins. I wrote neighborhood, you could have written boundary as well. So that's going to be our isoperimetric theorem in the cube, and as we'll see, it's got lots of consequences coming later. It's called Harper's theorem. Who actually first proved it? It's not quite clear. So for reasons I'll get to in a minute, Harper's original proof is incredibly fiddly, has lots of gaps in it. And you can fill some of the gaps, but you can't fill all the gaps. So probably the first person who ever wrote down a correct proof of Harper's theorem is probably Katona, whose name we'll hear several times in the sequence of things. But it's called Harper's theorem. The name is there to stay. That's just life. Okay. So that's what we'd like to prove. Of course, what do you really care about in there? The interesting case is the case of levels. So I could even write, in particular, this is really what you really care about. In particular, if the size of A is x at most r, I don't write some whole binomial sum, but we could, of course, right? If the sum from 0 to r of x choose I, then the size of the neighborhood of A is at least what it is for that thing there, x at most r plus 1. Okay, So that's what we'd like to prove. I want to make a couple of remarks about it before we get on and prove it. So sometimes people use the word, something like a metric ball for something like this. And the kind of next best thing is what you might call a Hamming ball. So here's the cube. Supposing my set has everything of size less than r and some junk on level r. Making sense? So some stuff in x brackets r. That's called a Hamming ball. So Hamming ball means anything that's between up to level r and up to level r plus 1, okay? So it consists of a total ball and maybe nothing, maybe some junk on the next level. Now, if we knew that we are Hamming ball, so if A is a Hamming ball, so if I promised you my set's a Hamming ball, then if you think about it, what is the neighborhood? So again, everything up to r, something on level r. What's the neighborhood? Everything up to and including level r, right? And some junk on level r plus 1, making sense? What is that junk? That junk is the kind of upper neighbors of points in there, right? It's all sets you can get from one of your r sets by adding an element. That's often called the upper shadow. So suppose A equals x brackets less than r union b, where b is this red bit. Then what we're getting is that the neighborhood of A is x at most r union what you might call the upper shadow. This is called the upper shadow of B. Make sense? So the upper shadow means everything one above you. I'm not going to write down formally. It's all sets you can get from a set in B by adding an element to it. Okay. So, if we took Harper's theorem, suppose you know Harper's theorem, I said to you, okay, what does that tell you when A is of this form? Answer, it would tell you that if you're picking some stuff in level R, 10 things in level R, and you want to minimize the upper shadow, take the same to Lex. That would follow from Harper's theorem. So we'd get, if I have a set B in XR, to minimize the upper shadow of B, choose an initial segment of Lex. That would follow, right? That would follow from Harper's theorem. And conversely, of course, if you know this statement, you don't know Harper's theorem, but you would know Harper's theorem for a Hamming ball, right? So if I promised you my set's a Hamming ball, then you would say, okay, my set is everything below R and some B. Trying to prove Harper's theorem. You'd say, what's the neighborhood? Everything at most R and the upper shadow of B, which by that fact is minimized by that. So again, this fact here would follow from Harper's theorem. It wouldn't prove Harper's theorem, it would prove Harper's theorem if you knew you were a Hamming ball. And this is often called the Khachatrian theorem. So in other words, having proved Harper's theorem, we'll instantly know the Khachatrian theorem is a conclusion. Just by the way, people often like to talk about KK as going down, not up. So there's an equivalent form of Khachatrian for shadow going down, which I'll just mention. So this is a sort of somehow the more usual form of KK. Do you remember I said that if you take complements of Lex, you get colex? So if I took this theorem in level n minus r and took complements, that would replace upper shadow by lower shadow, which is called shadow. You'd get the following. You'd get that if you have B in XR, then to minimize the lower shadow of B, often it's called the shadow, that's called the shadow, use an initial segment of colex. Okay, where again, the shadow, it's normally called the shadow, or what's called the lower shadow, is everything you can get from something in B by removing an element. Because that corresponds to adding element, you take complement. So again, so if you like in symbols, the shadow of B is the set of all B, of all X, take away the element I, such that X is a set in B, and I belongs to B. Does that make sense? You take everything in a level, remove an element everywhere you can, that's the shadow, and that's Erdos-Ko-Rado. That's the more usual form of KK than that, actually. So most books, if you see KK, it'll be this one. So first, let it be this one, let's group to that one. So what we're saying is, again, if you've proved Harper, you instantly prove KK. Converse is not true, but by the way, if you knew you were a Hamming ball, then KK would give you Harper. So if you've met KK already, then you might believe Harper's theorem. We're going to prove Harper's theorem now, and therefore you all know KK. Okay, so how to prove Harper's theorem? So now I'm going to prove Harper's theorem. So the original proofs were kind of incredibly yucky. They first said, let's write down a formula for how big the neighborhood of C is. That's really disgusting, right? And if you're lucky enough that your size is exactly at nice levels, then that's easy formula by limit coefficients. But if your thing is, let's say, up to level R and 10 points next level, you would need to know, yes, it's the 10 points in Lex, but how big is their upper shadow? That's some disgusting thing. So you first had a horrible calculation of neighborhood of C, and then you took your A, and you tried to say, well, if it looks like this, then do that, and if there's this case over here, do that, and let's try and count it up, and if that was happening, you could do that. Lots of cases fiddling around, and there's too many cases, basically. So all the original proofs were all just wrong, because they all just said things like, do this and this and this, we're done unless one of the 6 bad things happens here, and there's many more bad things. So the original proof is quite horrible. In the modern viewpoint, so I'm saying modern, maybe before you guys were born, so these theorems in the 60s, modern viewpoint means basically from about 1990 and afterwards. In the modern viewpoint, the key idea is to be as lazy as possible. So you absolutely do not want to ever calculate any disgusting things here. You want to see what's going on and be lazy. So well, let me show you the rough idea of what we're going to try and do. So we have our A being compared to our beautiful C. So what you'd like to massage A, you'd like to transform A in some way. You'd like to send A to some A prime, also in the cube, of course, and you'd like it to somehow make progress. So what you would like is, so this is a bullet mark, in case you don't know, it's an exciting bullet mark. First of all, of course, the size is the same. Secondly, you didn't increase the neighborhood. And most importantly, in terms of making progress, you'd like A prime to look more like C than A did. So A prime, quote, looks more like C than A did. Do you agree that we progress? Because again, we're trying to compare A to C. Now, look at A prime. A prime looks more like C, and therefore, hopefully, in a dream world, easy to compare it with C and show that C beats it. Of course, if we know that C beats it, it follows from the second bullet mark that C beats A as well. Does that make sense to everyone? This is called a compression operator. It's called a compression or compression operator. Of course, we're going to say what the operator is going to be, but by compress, I mean make it look closer, make it look more like a simplicial ordering initial segment in some way or other. And in a dream world, you'd find a family of these. You'd maybe send A to A prime, then have a different clever operation, A double prime, and so on, hopefully terminating, not looping, until eventually you've got some winning system over here, B, that maybe was equal to C. Right? Do you agree? If I can compress, 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 always decreasing the neighborhood, and make it into C, we're definitely done. Okay, maybe we're not equal to B. Maybe we're so close to C that it's obvious that C beats B. Make sense? That's going to be the aim. So that's what I mean by being lazy. We never want to say, if C has K points, what's the formula for neighborhood of C? We don't do these compressions. Now, what is the best compression in the world? It's the following exciting thing. It is the operation replace A by C. Now, this is correct, and this is certainly correct, but we don't know this is correct, right? Because that's the thing we're trying to prove. So what I mean, of course, is that we can prove this statement, not just it's true. All right. However, that rather silly sentence gives us our key idea. So what we'd like to do is replace A by C itself. That's sadly not allowed. What's the absolute next best thing? That'll be I say take the whole n-dimensional A and make it C. Let's do the same in the two n-1 dimensional subspaces. So the idea is going to be, I'll start drawing in a moment. We're going to take our A, we have some direction n maybe. We have upstairs hypercube, downstairs hypercube. In each of those, we're just going to replace my initial segment. And we'll see what that does to us. This is something called a codimension 1. So we're going to look at a thing called a codimension 1 compression. There are many other compressions you can do in Harper's theorem. So initially in the 80s, people found compressions that made this proof work, but they were quite complicated to analyze. And then gradually people realized that, wait a second, let's do the biggest, baddest compression possible, makes everything super nice. So this is going to be actually a very, very short, clear proof of Harper's theorem because of this big, big compression. So let's see what the big compression is. Let me now try and draw it. And remember that when we proved Harper's theorem, we'll also prove Erdos-Ko-Rado. And what I forgot to say was that both Harper's theorem and its corollary, Erdos-Ko-Rado, are going to be important for us in later lectures. Okay, so here's the idea. Pick a direction I of the cube. That breaks up the cube into two subcubes, right? Suppose I had Q4 initially. I would have, it's so hard to draw. So I'm sorry for my horrible picture. So do you agree I've drawn you two copies of Q3? Making sense? So I'm in Q4, pick a direction, maybe it's the vertical direction. So here are my two Q3s. I'll draw you my set A. It's got maybe 3 points upstairs and 4. So that's my A. Is that making sense? Now, what does the compression do? The compression, which I will call C sub I of A. So C sub I, it says, that's what I just said. You take your cube, direction I, break into two copies of Qn minus 1. In each of those, look what you have, and replace it by, in n minus 1 dimensions, the thing you think is the winner. So it goes to, let's see what it would go to in this case here. So I'm drawing you Q4. Remember, of course, officially Q4 has also vertical edges. I'm not drawing those to avoid making the picture look horrible. Okay, so what would the set Ci of A be? We'd say, on top, I see 3 points, replace them by the first three in simplicial, which is the empty set, singleton 1, singleton 2. On the bottom, it's 4, so making the first one simplicial. Make sense? Like that. So that's the compression direction I. Okay, officially, I've left something out because being super, super formal, if my initial thing was power set of 1, 2, 3, 4, 5, and I is 3, these are not actually literally Q4, they're the power set of 1, 2, 4, 5. But obviously that's obviously isomorphic to a cube, and obviously you know what simplicial means there, right? So officially, I should have said that on the power set of 1, 2, 4, 5, simplicial is fine the same way, go up by levels, in level, use small elements. I hope you should allow me to do that. Great, good. Another important point, by the way, is that when I said deal with the upper part, so I could have drawn this. I wonder if blue is visible. Is that letter visible? No, okay. We may just give up. Let's try this orange. This orange. Is that visible? And is it clearly neither red nor white? Amazing. So I'd call this set here A plus, and this one here A minus. Does that make sense? So officially, A plus and A minus live in the three-dimensional cube. Right? Okay. And so the official rules are, in symbols, you would say, given a system A, here's how you form a new system. In the things without element I, replace by the first A minus in simplicial on the cube one dimension less, pause. Amongst the things with element I, another subcube, replace what you have, A plus, by the first A plus things in simplicial. That's the compression. Now, this one's trivial, right? I didn't change the number of points. Okay, this one, okay, it was informal. Hope you kind of believe it. And it's very close, isn't it? When we do one compression, suddenly, in the entire QN minus upstairs, you look like exactly the winning set. And same downstairs. So it must be a good thing to be doing. Now, let's see if we can prove this one. Prove, of course, rather than just hope it's true. So let's have a go at doing that. So let's try and write out how big the neighborhood of A is. I guess with the size of the neighborhood of A. So the neighborhood of A, of course, has some downstairs junk and some upstairs junk, right? What is the neighborhood of A downstairs? How would you get a point in A or adjacent to A? Well, first of all, it could be in the actual neighborhood of A minus viewed in Q3, right? So you could be in. I'll write the unions. Is the neighborhood of A minus, but also, of course, remember, there are edges vertically, right? So a point up here gives the same point there in the neighborhood. Is that making sense? So if we're going to clear out that, it's the same point, right? So what I'm saying is, if the point 137I is upstairs, then 137 is in the neighborhood. Do you agree with that? So literally, you union it with A minus. That's the upstairs part. So this is, if you like, neighborhood of A upstairs. Sorry, downstairs. So just say it again. The neighborhood of A downstairs is the union of two things. You could be either in the set or adjacent downstairs, say downstairs. That's neighborhood of A minus. Or you could be literally the set A plus. Right? And that, yes? Oh, I'm so sorry. Thank you very much. Thank you. Thanks. Literally, it's not native, it's literally A plus. So I'll say it again. If here I have the point 1, 2, 3, I, that means that 1, 2, 3 belongs to A plus. A plus, we're living in that world. That tells you that 1, 2, 3 belongs to the neighborhood of A in the lower part. And similarly, neighborhood of A minus, plus rather, is the upstairs part, neighborhood of A plus, together with whatever comes from below. That making sense? Okay, good. And of course, the same thing happens for C, right? Exact same formula hold for C, because it's true for any set. So similarly, the neighborhood of C minus, is the neighborhood of C minus union C plus, and the neighborhood of C all plus is the neighborhood of C plus union C minus. All right. Now let's start thinking. What do we know? A plus has the same size as C plus. Agreed? Because that's how the question is defined. How about the neighborhood of A minus versus neighborhood of C minus? Well, that's bigger by induction, right? By induction on N, Okay, so we check Harper's theorem for the dimension Q dimension 1, or if you're a totally sad person for dimension 0, it's going to work, so we do it by induction, right? Because in Harper's theorem in dimension n minus 1 would literally say you take 17 points, you take the first 17 in simplicial, that's got smaller boundaries, or neighborhood. Okay, so this is equal to that, and this is at least that. But the important thing is, these two sets are nested. It's an easy check that the neighborhood of an initial segment is an initial segment. So think about it a bit. For example, the neighborhood of this initial segment, all points up to level R, is everything up to level R plus 1, also initial segment. Just believe it's easy check. Neighborhood of simplicial segment is simplicial segment again. So, this is bigger than to this. These equal size, but these two are nested. They're one inside the other, right? Because they're each initial segments of simplicial. Do you agree with that? If I give you two segments of simplicial of sizes 10 and 17, the union has size 17, right? Whichever one's bigger, that's the big thing. So these two are, let me just say nested, which means one's inside the other. Oh, I'm so sorry. Thank you. I'm pointing at A. Sorry, thank you. Yes, C. Thank you. So these two, let's try again. These two are nested. And if they're nested, it follows that this set is smaller than this set. And think about it for a second. If my sets are size 10 and I've got two sets size 10 and 17 that I'm unioning. Here, I get 17, because whichever one's bigger. Here, I get, I don't know what I get, but any time you have a 10 and a 17, you use at least 17, right? So that's certainly fine. So the conclusion is, by the induction hypothesis and the fact that initial segments are trivially nested, we get that this is smaller than that. In the same way, that's smaller than that, and so we're done. Yes?
Yeah. Moving back about the neighborhood. So here you're taking neighborhood of A and then looking at the lower part.
Yes. Yes, that's true. That's true, but here's the point. The neighborhood of A minus is this set union that set. I'm just looking at the lower part neighborhood of A, the minus part. It's this union this, we agree? And for C, the lower part is this union this.
Or rather, I don't see it. I don't see why so A plus is a guy that has coordinate A. Right?
A plus is the points upstairs, but viewed without having, but viewed as a subset of Qn minus 1. So they don't officially have element I in them. So in this case here, A plus is empty set and singleton 3 and 1, 2, 3. Because remember, I view them as living inside Q3. I don't want to think of A plus and A minus living in Q4. I want to live in Q3. It's okay? Okay. So this is smaller than that, that's smaller than that, and so we're done. Because the total neighborhood is what you get upstairs, what you get downstairs. Okay, great, so that's a good start. So we found a compression. Okay. Let's now try and find a lot of compressions. Well, of course we can, for each direction, right? Now, of course, maybe when you do C1 first, maybe when you do C2, you mess up C1, it's no longer compressed anymore. You do it again, that's fine, just keep doing them. So now you do A, you go to A prime, you go to A double prime, and so on. Each time the rule is, I'll say your I compressed means you've done that already. I compressed means upstairs and downstairs initial segment. Okay, so let's say that I compressed means Ci of A is A. Does that make sense? So I compressed literally means your upstairs half is an initial segment, and so is your downstairs half. So particularly if you do an I compression, then you get I compressed. So what do? You keep applying compressions. You apply C1, C2, C3, back to C1, just keep going. So the official rules would be, if you're at some stage, A triple prime, and there's an I where you're not I compressed, I compress it. That's your a quadruple prime. If you're I compressed for all I, then you stop. Making sense? And this must stop if you think about it, because you're always moving things to earlier in simplicial. Right? If you think about that, if I added up for each point where it is in simplicial ordering, that goes down. You're moving things early in simplicial. So you can't, no cycles happen. Right? So this terminates because some quantity keeps going down. You could, for example, add up for each point its position number in simplicial ordering. That obviously that goes down straightly. So it terminates. Great. So now we have a wonderful set B living in Qn with the following properties, this final thing. First of all, size of B is size of A. Secondly, size of neighbourhood of B is at most size of neighbourhood of A. And most important of all, B is I compressed for all I. Make sense? By repeating this, okay. And so if we can just show that B is beaten by C, then of course A is beaten by C, because of that thing there. Actually, does B have to equal C? That's the first thing you've done. Maybe you've done enough compressions in our dream world that if you're I compressed for every I, you actually are C. Then we'll be done, right? If I could tell you, therefore B equals C, you're done. So my question would be, I give you a set system, meaning a family of sets. It's I compressed for every I, meaning on top and bottom it's simplicial intersegment. Left and right, front and back. Is it simplicial? And Sally answers no. If you think for about 10 seconds, you'll come up with the example I gave you right at the beginning, in fact. Do you remember the non-winning 4-point set? It was this one. Do you remember this set here? Do you agree that's not the first 4 points of simplicial? Because that would be empty set 1 and 2 and singleton 3. But do you agree that on the bottom it's an initial segment? It's the entire Q2, right? On the top it's empty, that's an initial segment. On the front, it's the first 2 points of Q2, isn't it? It's empty set and singleton 1, but not 3. On the left, on the right, front, back. In every case it is. So that's a very, that's very miserable, that's very sad. So you'd guess the work's going to start now. So now we're going to say, now comes the work for Harper's theorem. We've done the easy stuff. We've done this general fluff nonsense for compressing. We have a set that's I compressed for all I. Now comes the work, it's beaten by C. But something weird happens now. This is definitely a counterexample, right? If you try and find a second counterexample, you kind of find you can't. So what I'm going to claim now is that actually, if you're I compressed for all I, then either your simplicial will be done, or there's exactly one counterexample for each n. And of course, in that one example, it'd be a trivial check that we beat C. So let's do that now. So here's my claim. If B isn't exactly C, then there are two cases. Either n is odd, and let me draw you what B is. So let me draw you the cube. The cube has two middle layers, right? It's got the middle layer here. Let's suppose n is 2r plus 1. So here's level R plus 1. Now, and your segment would be everything up to level R. I'm going to take that, I'm going to remove its last point and add the first point there. Okay, so lose, add. Does that make sense? I could write it in symbols, yawn, right? I could say it is, you know, what is the last thing on level R? I guess it's the R set, which is n and n minus 1 down to n minus r plus 1. And I could write, and the first thing here, it's the r plus 1 set 1 after r plus 1, right? I'd rather say last, I'd rather draw it as last and first. Could I do that? Thank you. Either, and B equals this, or, Oh, by the way, in that case, what is C? Just the ball, isn't it? Hope you agree it's a trivial check. In that case, B is beaten by C. Because if you move this here, you basically gain nothing at all in its upper shadow, but you lose masses in upper shadow over there. So, yeah. Or, n is even. Suppose n is 2r. And now B equals. So here's what we're going to get. We're going to get everything up to level R. And in level R, I'm going to take the half of it that involves a 1. So this is things with a 1. Do you remember that on a level we use lex? So you do everything with a 1 for everything without a 1. I'll take everything with a 1, and I will then, again, lose and add. Does that make sense? So I lose, literally, the one final R set that contains 1, which, if you think about it, is 1 and n minus 1 down to n minus r plus 2. Make sense? And you add the very, very first thing with a 1, which I guess would be, do that again, sorry. We remove the last thing with a 1, which I just said, and you add the first thing without a 1. What's the level? It's 2, 3, 4 up to r plus 1. Does that make sense? If I write horrible massive symbols on the board, I don't want to write that. Okay. And again, it's an easy check that in that case, if you replace this by this, I make it C, you get better. Hope you can see that. Because something without a 1 is getting lots of new stuff. This thing's already covered. It's basically a very easy check. Okay. So last minute and a half, we're going to prove this. There's only exam, and then we'll be done, right? So how do we prove this? And it's strangely simple. Say it again? Yes. No, it's of this form. It's literally the 3 cube. I removed the last singleton, namely 3, and added the first pair, namely 1, 2. So you take the empty set 1, 2, and 3, you remove 3, you add 1, 2. Sorry, morally you're right. It should be nothing like a hyperplane, but it's a hyperplane in that case. So why is this true? Well, here is the world called simplicial ordering. Now, if you're not in a segment, you must have some x that doesn't belong to B and some later y that belongs to B. Does that make sense to everyone? Again, not, so it means if you look at the ordering of simplicial, there's something not in for something that's in. Fair enough? Right. Now, could you have some element 1 belonging to both x and y? Answer, no way. Because if 1 belongs to both x and y, then direction 1, x and y are both upstairs, right? And we know we're simplicial upstairs because we're compressed. Does that make sense? So this is a no. Could 1 belong to neither of x and y? Could you have both? You can't, can you? Because if 1 belongs to neither x nor y, then direction 1, they both live downstairs, right? And downstairs, we're in a segment, simplicial. So you can't have that. Does that make sense to everyone? Great. So what does that tell you? That tells us for every direction, I belongs to x or y, but not both, which says they're complements. So that implies, sorry, I mean, not with 1, that and the same for each I implies that x is y complement. So here's what that tells you. Take any y that's in B. There's probably an earlier thing not in B. There's at most one such thing, right? Because everything earlier which isn't in B equals y complement. And similarly, take this x isn't in B. Of course, something later might not be in B. There's only one thing, because every z later in B has to equal x complement. So these are actually adjacent, aren't they? You can't have a z in between. Because if it wasn't in B, you contradict this way. If it is, you're that way. Therefore, they are adjacent. In simplicial. Now, when does that happen? When does it ever happen? You have two things you waddle in simplicial. Empty set, 1, 2, 3, 1, 2, 1, 2. When does it ever happen that you waddle for a set to its complement? If it never happens, then this can't happen at all. When does it happen? Well, think about it. You go up in levels, don't you? Suppose n's even for a moment. So suppose n's odd. You go up in levels. So inside a level, you can't go set to its complement, can you? Because twice the size can't equal n. The unique time in odd-dimensional cube you go for its complement is when you go from the end of R to first R plus 1. Does that make sense to everyone? It can't happen any other time, can it? It can't happen for two things down here, because they're both small and half size, they're not complements. It can't two things up here. It can only happen when you jump between those two. Now, it so happens, accidentally, it is true that the last thing, sorry, up this picture, n odd. It so happens the last thing is the complement of that thing there. So that's my example. If it didn't happen, the answer would be there's no counterexample. So that's the n even case. How about the n odd case? When does it happen? You waddle in n odd. Suppose n is 10. So n's even now. You're going up in Q10 in simplicial order. When you ever step from a set right to its complement, it's not from a 4 set to a 4 set, right? Because that's too small. It's not from a 3 set to a 4. It's got to be from a 5 to a 5, right? Otherwise, you're too big or too small. When does it happen, if ever, that in simplicial, i.e. in lex, on the 5 sets or a 10 set, you step from a set to its exact complement? Well, remember that you do everything with a 1 for everything without a 1. Agree? So the unique possible time you could ever go set to complement, when you go from last with a 1 to first not without a 1. And if you check it, they are complements, this can happen. If you don't want to check it, you say, fine, either that's counterexample or there's no counterexample. So we're done. It's very, very weird. You have this nice, lovely, clean compression idea, which sounds fantastic. You have this hiccup or feeling of horror. Oh dear, we're not done at all. Because if you're compressed, you may not be. But then luckily, you're done. Because it's only counterexample. So what this show, so there are many other compression proofs where you compress in single directions, things called, you have things like IJ compression or shifting. Those all work, but they don't do enough. The point, these k-dimensional one, they do so much of the compression, we left there's almost nothing. Okay, so that's the end of today. We've done Harper's theorem, we've done KK. If you want into details of things I just said needs to check, you can look at the printed notes. And then there are examples this evening, this afternoon, and then tomorrow we carry on with Intersecting Families. That's the end for now.